today we are reviewing very important formulas from electric potential. The first formula right here is work done by the conservative force. This WAB is the work done to bring a charge from one point of space to the another point from A to B, which is equal to VUA minus UB. UA is the potential energy at initial position and UB is the potential energy at final position. So which is equal to, if we rearrange this system, this will be negative UB minus UA, which is negative delta U. This is the negative of change in potential energy. So work done by a conservative force will be equal to negative of the potential energy. The second equation is the electric potential energy of 2-point charges, which is denoted by U and given by 1 by 4 pi epsilon naught. This epsilon naught is electric constant and Q2 and Q0 are values of two charges, where R is the distance between two charges. The third important equation is for finding electric potential energy of point charge Q0 and a collection of charges Q1, Q2, Q3 and so on. There might be more than these forces. If there are collection of the forces, then electric potential energy of point charge and all the collection of other charges will be given by this equation. U equal to Q0 divided by 4 pi epsilon naught, where this Q0 is the point charge and all charges over here from Q1 to Q3 and so on. These are charges, collection of charges, and at the bottom R1, R2, R3 and so on. These are the distances from Q0 to individual charges Q1, Q2, Q3 and so on. Or we can write down this equation in this form: Q0 divided by 4 pi epsilon naught summation I Qi divided by Ri. Here is another important equation that relates electric potential to a point charge. So this is denoted by V, capital V, and given by V equal to 1 by 4 pi epsilon naught, where epsilon naught is electric constant again, and Q here is the value of point charge and R is the distance from point charge to where potential is measured. So this is the distance from the point charge. This is the point charge. Suppose you have to find the potential right here, so this distance is R. Okay, going down, electric potential due to a collection of point charges. If there are more than one point charges, what will be the electric potential? You simply add all these charges divided by distances from the point charge to where you have to find the distance, right? So electric potential due to a collection of point charges denoted by capital V is equal to 1 by 4 pi epsilon naught summation I Qi Ri. Qi is the value of ith point charge and Ri, this is the distance from ith point charge to where potential is measured. The next, electric potential due to a continuous distribution of charges. If there is a continuous distribution of charges rather than point charges, you have to take integration. We need integration. So the potential due to a continuous distribution of charges V will be equal to 1 by 4 pi epsilon naught integration dq by dr, where dq by integration dq by dr is integration over charge distribution, and dq, this is the charge element, and r here is again the distance from charge element to where potential is measured. In this case, the distance is from the charge element, because charge is not discrete, right? It is something like continuous distribution of charges. We have to take little charge distribution, that is dq. So this is the distance, this r is the distance from charge element to where potential is to be measured. Next, electric potential difference. So this is simply the potential difference between 2 points, which is denoted by VA minus VE. This is simply the potential difference, that is electric potential difference between points A and point B. This is equal to integral along a path from A to B, and then right here is the scalar product of electric field and displacement vector, right? If we integrate, take the integration from position A to position B to the electric field strength with this element, then you will get the potential difference, which is equal to integration from A to B E cos phi dl. This phi is the angle between E and this dl, and E is the electric field again. Electric field components found from potential. We can find electric field from the potential. So right here are the components, x components of electric field, y components of electric field, and z components of electric field. This is not x, so let me correct it. This should be v, okay? Because to get the electric field components, we have to take partial derivative of the electric potential, electric potential, right? This is the potential, and we are taking the partial derivative. This is the x component of the electric field, this as a whole, and this one is y component of the electric field, and finally z component of the electric field. Okay, so electric field components will be equal to the negative of the corresponding partial derivative of electric potential function V. Look at here, this is the negative of partial derivative of the electric potential function, this V, right? So you are getting x component, y component, and a z component. If you need to find the electric field as a whole, I mean adding all the components together, Ex, Ey, and Ez, you will get the electric field vector found from the potential, which is negative sign can be taken common, and delta V by delta x, x components, plus delta V by delta y, z components, and delta V, this is again V, divided by delta z. Okay, so this one gives you the electric field vector found from the potential.